Okay, good evening. So I'm audible. So let's continue. So do you have any doubt?
Recording in progress.
So if you have any doubt, you can ask. Or did you complete last question? So I think last time we had some problems, so that's why I could not complete class. So no doubt. Okay, let's continue new topic. So today actually we'll discuss this topic. Sampling distribution is left. Huh? So today we'll start with sampling distribution, then characteristic function. So start with so in sampling distribution actually we have to first define a random sample. So what is definition of random sample? So actually, let's say random variables x1, x2, dot xn is said to be a random sample of size n from a population with PDF or PMF. You may write notation x theta, so it's or x just theta, or usually I write it f theta x something. So this is PDF of sample. So this is PDF of x1, x2, xn, all random variable. So if an random variable x1, x2, xn is said to be a random sample of size n from this distribution, if and only if x1, x2, x3, xn are IID random variables. So they are actually IID random variables with, so they are IID random variables with common PDF or PMF. You write fx theta, or you just write, or you may write f theta x. Okay, so this is definition of random sample. So random sample means IID random variables. You can simply understand. So random sample means it is IID random variables. In short, so in parametric inference, so if you write random sample, so that means they are IID random variables. So okay. So if you write, let me define some, let's say statistic. So what will be a statistic? Because sampling distribution, so we have to actually find let me write sample mean and sample variance. So let me define sample mean and sample variance. So let x1, x2, xn be a random sample. from a population so x1 x2 xn be a random sample from a population with mean mu and variance sigma square. So actually just mu is actually population mean, sigma square is population variance. So actually just I want to tell here mu is will be called population mean. So this is population mean and sigma square is actually population variance. Okay, so mu is population mean, sigma square is population variance. So we have to define sample mean. So sample mean is actually x bar, you know already, x bar is defined as 1 by n summation xi I from 1 to n, and sample variance s square, it's 1 minus n minus 1 upon n minus 1 summation xi minus x bar whole square I from 1 to n. So this is the definition of sample variance. Further if I write a theorem, so further I can write properties, theorem or properties. So you can find expectation of x bar will be mu. If you find variance of x bar, you will get sigma square. It's very easy to calculate. You just a simple algebraic calculation. And the third, if you find expectation s square is sigma square. And the fourth one, if you find variance of s square, so that will be 1 by n mu 4 plus or minus n minus 3 upon n into n minus 1 sigma 4. Okay, so this is where mu 4 actually, so where mu 4 is fourth central moment. And what is fourth central moment? It's expectation x minus mu raised to power 4. Okay, so this is the story of sample mean, sample variance. So sample mean will always be unbiased estimator of population mean, sample variance will always be unbiased estimator of population variance, and variance of sample mean is sigma square by n, variance of sample variance is 1 by n mu 4 minus n minus 3 upon n minus 1 sigma 4. So in general, for any distribution, you take sample from any distribution, this will hold. Okay, if you write for the normal one, so let x1 x2 xn, this is a random sample from normal distribution with mean mu and variance sigma square. Okay, so this is mean mu and variance sigma square. So now then so x bar will have distribution normal with mu and sigma square by n. Second, so here you can also write like simply if I write, so expectation of x bar is in general mu, so it will be also for normal population, and variance of x bar, it's a sigma square by n for any population. So like if I write here fourth one, expectation of s square, it's again sigma square, variance of s square, so here it will be reduced to 2 sigma 4 upon n minus 1. So if you simplify this one, so if you find fourth central moment in the normal. So that will be 3 times sigma raised to power 4. Okay, so that will be 3 times sigma raised to power 4. And if you simplify it, so I think after simplification you will get this. And the sixth one is n minus 1 s square by sigma square will have distribution chi-square with n minus 1 degree of freedom. Okay, so this is something like, further you can write summation xi minus x bar upon sigma whole square I from 1 to n. And fifth one, if you write distribution of xi minus mu upon sigma whole square, so these are some theorem, or this can be proved using transformation or basic manipulation. So this will be chi-square with n degree of freedom. So I think 1 2 3 4 5 6 7 8 x bar minus mu sigma by root n. This will be normal 0 1. Ninth, so if I write ninth one, x bar minus mu sigma by root n t with n minus 1 degree of freedom. 10th, so the 10th one is, what is left? X bar and s square are independent random variables. So okay, so see, these are some study of sampling distribution actually. So sometimes we take sample variance as 1 by n, we take, okay, so actually you are right, but sometimes it happens, but in the parametric inference sample variance is defined like this. And the intention behind this is we want this to be unbiased estimator. That this was the idea. So the modification was done with this purpose. So we wanted to have a sample variance to be unbiased estimator of population variance. That's why it was defined like this. But yes, sometimes like in descriptive statistics, if you have a data set x1 x2 xn, in that case you define like you have x1 x2 xnb n numbers. Okay, and then if they ask you what is variance, so here you define variance like this: xi minus x bar whole square I from 1 to n in descriptive statistics. Okay, so yes, but in the sampling case, or you say in inference, or especially in estimation theory, so in the estimation theory this is the definition of sample variance. Okay, and the purpose is this, but this in the descriptive, this is the variance and that is defined, but in parametric inference this is the sample variance. So everywhere you will find sample variance this only. Okay, you can go to any book like Rohatgi or Kasela Berger or any high level book, so you will see this is a definition of sample. This is a definition, so we are defining like this. Okay, and since I'm not defining, I'm just conveying to you from the books they have defined. Okay. Okay, so this is a theory, and there are many questions they ask on this, like in the sampling distribution, there are many results. For example, if I come to, okay, let's say chi-square distribution. So there are two ways to obtain chi-square distribution. One is through gamma distribution and other one is through standard normal distribution. Okay, so like gamma distribution, if we say let x has gamma distribution with parameter alpha beta, so the PDF of x, we have already defined this: gamma alpha x raised to power alpha minus 1 e raised to power beta x, x more than 0. So this is actually PDF of gamma distribution. Now, if we take alpha is equal to n by 2 and beta is equal to 1 by 2 for n belongs to natural number. So then x will have distribution, then x has chi-square distribution with n degree of freedom. With n degree of freedom. Okay. So what I mean? So means gamma n by 2. So gamma n by 2 comma 1 by 2 will be identically distributed with chi-square with n degree of freedom. So what will be PDF of gamma? So if I say PDF of chi-square n. So let x is a random variable now with chi-square distribution with n degree of freedom. Then PDF of x. So you just replace alpha by n by 2 and beta by 1 by 2. So you will have 2 raised to power n by 2 gamma of n by 2 x raised to power n by 2 minus 1. This x more than equal to 0. Okay, this support is x more than equal to 0. So if you find further expectation of x in the chi-square, it is n. Variance of x, if you find, it's 2n. MGF, if you find, it's minus 1 minus 2t raised to power minus n by 2. And okay, so here n is a natural number. Okay, so this is the one way you can generate chi-square distribution from gamma. The other way is, through normal distribution. So let x1 x2 dot 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 xn be independent random variables with each xi has a normal distribution with mu I comma sigma I square. Okay, for all I 1 2 3 up to n. Okay, like this. Now transformation. So what we have, so since xi is this one, so xi minus mu by sigma I will be normal 0 1. I'm just doing transformation that can be proved. Okay, so I think one theorem I left in last class, so let me just complete that. And that is a theorem of transformation that says so let x be a continuous random variable and y is a function of x. This is a differentiable monotonic function. Then PDF of y can be obtained as so fy of y is equal to PDF of x into dx upon dy. Okay, where correspondingly you can find. So this is a formula. You can further simplify it. So this will reduce to fx of x will be g inverse y and d upon dy of g inverse y. Okay, and that modulus. So this is the way you can obtain PDF of, like for example, y is x square and support of x is positive, then x square will be monotonic over support of x. In that case you can find PDF of y square using this formula. Or there are many theorem, like I have given x is uniform 0 1, then minus 2 log x is exponential half, that is chi square 2 also. So that can be proved using this formula. So you can obtain PDF of y from PDF of x. This is Jacobian in one variable case. You can also say like this, PDF of x into Jacobian, है ना? So here this Jacobian is dx upon dy. Okay, so Now, so xi minus mu I upon sigma I. So just using last formula, you can derive this type of things. There extension also. So allow this is not monotonic, but it can be derived. So this is chi-square 1, and if you take summation, so I'm saying whatever PDF of this random variable will be, that will be chi-square 1. Then xi minus mu I upon sigma I whole square, I from 1 to n, that will be chi-square with n degree of freedom, है ना? That you name something, you may name it something. So for example, so let's say this was z, है ना? This is z square, है ना? And this is just you can name something, or it's a zi square, it's a summation zi square. Okay, and I name it something, let's say it's a w, for example. So what I'm saying, that w has chi-square with n degree of freedom, and it is obtained from standard normal, so that you can see. So through normal you can derive chi-square with n degree of freedom, and then w will have same PDF, like what if you want to write in w or t or x, it's up to you. Okay, so that will be 1 upon gamma n by 2 2 raised to power n by 2 t raised to power n by 2 minus 1 e raised to power minus t by 2, है ना? T is more than equal to 0. So this is the formula. Okay, so now I think there is some problem. Okay, so we'll discuss so what is the problem in that? So there is simple transformation. If x is normal mu comma sigma square, then x minus mu minus sigma will be normal 0, 1. It's a simple. If you find expectation of this, you will get 0. If you find variance of this, you will get 1. So this is UG level things. I think you are, I think masters students, you should know all this. So simply if you do transformation, x has normal distribution mu this, then if you take x square, z square, so it's a x minus mu by sigma whole square. That theorem says a chi-square 1, chi-square with 1 degree of freedom. That can be proved easily through MGF or through transformation. So like if I, PDF of x, everyone know. So it's a 1 by root 2 pi sigma e raised to power minus half x minus mu by sigma whole square. X belongs to R. So using a last formula that I have written here, if I use this formula, I will use this formula, or you can use this formula to find. So if I want to derive PDF of Z, so according to that formula, PDF of Z will be PDF of x and dx upon dz. Now you simplify this and you write in terms of z. So you'll get 1 by root 2 pi e raised to power minus half z square, and z is a real number. Further, if you want to find, so there is a way, I'm just telling you, z square. So if you want to find PDF of z square, so let's say z square is something, you may name it y. But here actually it is not monotonic. Y is equal to z square is not a monotonic function. But it can be breaked into two parts, in negative part, positive part. So just I'm writing formula how to obtain PDF of y. So the formula is actually PDF of x or PDF of z. So z is plus minus root y, it's a root y, plus PDF of z at minus root y into 1 upon 2 root y. This is the formula. So in any case, if you want to find PDF of z square, so that PDF of y can be obtained like this. You just simplify it. So after simplifying, you'll see if you simplify it, you tell me what will be the PDF. So 1 by 2 root y is already there. And if you write both, you will have same thing. It's in 2 times 1 upon root 2 pi e raised to power minus half y. So after simplification, this 2 cancels. So it's a 1 upon root under 2 pi root under y and e raised to power minus y by 2. Y is more than equal to 0. So this is a PDF of that y. Y means chi-square with 1 degree of freedom. This is chi-square with 1 degree of freedom. PDF of chi-square with 1 degree of freedom. Now if I write, let y1, y2, yn, they are IID chi-square with 1 degree of freedom. So the result is, since I cannot prove all theorems here, we don't have much time, but you may try to prove, you may look into book and see how they prove. If you have doubt, then I can help in that. Okay, but I think you have to make efforts. You are all PG students, so either you know all this. If you don't know, you can learn. So then the result says yi from 1 to n, this will have chi-square distribution with n degree of freedom. So that I named w. Okay, so that I named w. So this is w actually, and PDF of w if you find, so like I have written there, so it will be 1 upon gamma n by 2 2 raised to power n by 2 e raised to power n by 2 minus 1, not e, t raised to power, or omega raised to power, e raised to power minus omega by 2 or w by 2 more than equal to 0. This is the story that I repeated here. It was same thing here. MGF of chi-square was this 1 minus 2t e raised to power. MGF is gamma. So what is MGF in gamma? In this gamma, I think 1 minus t by beta raised to power minus alpha. So 1 minus t by beta raised to power minus alpha. This is the MGF. Okay. So now this is the study of chi-square distribution. Okay, so chi-square, sum of chi-square is chi-square. If I write theorem, so actually the definition of t distribution actually. So if you like, we have defined how chi-square is derived from gamma and how chi-square PDF is derived from normal distribution. Similarly, t distribution if you define, so there are two way you might have seen someone Fisher's t distribution, a student's t distribution. So there are two theorem that gives distribution of t. So one is through x bar and other one is through. So both will have common PDF. Just there are two different way they have defined. Like we have defined, we have given two different way to reach to the chi-square PDF through normal or through gamma. Similarly, there are two way to reach to the PDF of t, and one is a Fisher's t distribution, other is the student t distribution. Like the way there are two theorems are there, or two methods are given, but both will reach to the same PDF. So PDF is common, it's a t distribution only, but Fisher and students are just name of the author, they have given the theorem or result. Okay, so how t distribution comes? So here it is, let z is normal 0 1 and let's say x or y, whatever you want. So let's y is chi-square distribution with n degree of freedom and both are independent random variable. So independent random variables. So z is normal 0 1, y is chi-square n. Then we define a random variable. Yeah, then a random variable t is defined. So t is defined with the help of z and y, and that will be z upon root under y by n. 1 minute. Okay, so how will you find the PDF of t? We already know the PDF of z. We know PDF of z. This is given here. This is PDF of z. We know PDF of t. T is chi-square with n degree. Sorry, y. which is chi-square with n degree of freedom. So we know PDF of y here, I mean z defined here. This is a PDF of y, that chi-square n. So with the help of these two PDF, how we can get the PDF of t? So there is again Jacobian method in transformation. Actually in a study class we could not, we just discussed 1 hour class, it was 2 hour, but so that's why few things I didn't discuss, like so this is the Jacobian method for transformation of single random variable. If we discuss the Jacobian method for the transformation of two random variable, that will be like this. So let xy be a random vector, and if so u is some function of xy and v is some other function of xy, let's say, so some function of hxy, or let's say g1, or we call it h1 for example, or we may write it g1 g2. Okay, it's better we write g1 g2. So u is g1 xy and v is g2 xy. So xy be a random vector if u is g1 xy, v is g2 xy, such that unique है ना, uniquely such that, this I'm writing in my own language. In book you can see they have their own language and own restrictions. Okay, so so such that we can obtain x which is some function of uv and y, so it's not g2, let's name it h1, and h2 uv uniquely matlab it should have a unique inverse. So that's why there why we have taken this restriction, monotonic. So monotonic function is differentiable function. I have taken monotonic function is invertible function. So if you have monotonic function, it will be invertible, it will have unique inverse. So that's why this condition is applied here, so that you can get the unique inverse of this. Okay, so so we have taken here u and v are this. So if you solve these two equations, so currently we have u and v in terms of x and y. So after solving these two equations, you can uniquely find x and y in terms of uv. Okay, so uniquely then, so PDF of, there are some more restrictions, but you try to understand what I want to convey. So we want to PDF of uv with the help of we want to find the joint PDF of uv with the help of joint PDF of xy. So that formula says it's a PDF of x comma y, again it is a continuous actually, so this will work only for the continuous random vector. So be a continuous random vector. Okay, so now this is mod of Jacobian, so that will be f of uv fxy xy mod of Jacobian. And what is Jacobian here? So in the two variable case, that Jacobian is derivative of old variable by new variable, and there is also same thing, you can remember old by new. Old by new means initially we have x, new we have defined y. So similarly old is xy, we are defining uv, so uv, and that will be 2 cross 2 determinant. So that is the determinant, del x by del u, del x by del v, del y by del u, and del y by del v. Okay, so so this is the way. So this formula will be used here. So what we'll do, since Z and Y are independent random variables, so joint PDF of Z and Y is the product of marginal PDF of Z into marginal PDF of Y. So we got the joint PDF of XY. So T is defined like this. We will define some other random variable. Let's say W, for example. I will take something like W. I will take, let's say, Z only, no problem. So we'll find joint PDF of T and W using that Jacobian formula. So we have to find joint PDF of T and W with the help of Jacobian formula. After getting joint PDF of T and W, we'll find the marginal PDF of T. And the PDF we'll get is the PDF of T distribution. So that is the idea, okay? So how it is derived. So then a random variable T is defined as and distribution of random variable T is T distribution. Okay, so capital T is the random variable, small t distribution. Okay, so distribution of random variable T is T distribution with n degree of freedom. So it's n degree of freedom. Okay, so what will be PDF of T then? So if you find moreover PDF of T is, so if you find PDF of T, that will be gamma n plus 1 by 2 gamma n by 2 gamma 1 by 2 is root pi into root T. That will be 1 plus, I think I have to see, T square by n raised to power minus n plus 1 by 2, and T will be a real number. So let me just check. So okay, that's fine. So this is the PDF of T distribution. Okay, so root 2 is inside square root, and further, if you further use, so what will be, so if we say T is a random variable with T distribution with n degree of freedom, expectation of T will be 0, n should be more than 1, variance of T will be n into n minus this for n more than 2, and the one observation simply you can see, if you put here n is equal to 1, so if you put here n is equal to 1, so you will find T with 1 degree of freedom is identically distributed with the standard Cauchy distribution. So if you put n is equal to 1, it will give you Cauchy 0, 1. Okay, so it will give you Cauchy 0, 1. So T1 is Cauchy 0, 1. Okay, Now so that's why for n is 1, mean and variance will not exist. Even for n is equal to 2, mean variance will not exist. So this is the way we defined t distribution actually, or we obtain PDF of t distribution. How we obtain f distribution? There is again idea. So how we obtained f distribution? So f distribution is like let x is a chi-square distribution with n degree of freedom and y is a chi-square with m degree of freedom. Okay, so x is a chi-square with n degree of freedom and y is a chi-square distribution with m degree of freedom. Now so it's chi-square with n degree of freedom, y is chi-square with m degree of freedom, and they are independent. They are independent random variables. Then we define a random variable, then a random variable, you can name it something, anything you can name it. हाँ, so चलो मैं W ले लेता हूँ, कुछ भी ले सकते हैं ना आप, कोई भी अल्फ़ाबेट ले लो, ये कुछ भी है ना, एनीथिंग वी कैन टेक, V मान लो या कुछ भी ले लो. सो F ले सकते हो. सो रैंडम वेरिएबल F था ना, तो ये थोड़ा रिपीटेटिव हो जाएगा, तो इसमें हम लोग ठीक है जी, F डिस्ट्रीब्यूशन है ना, कोई बात नहीं, W ले लेता हूँ. सो दिस इज X by M, Y by N. So again the similar idea is here. So W we have defined with respect to X. So we already have joint PDF of XY. Again we'll define something V as X. Then W and V joint PDF can be obtained from Jacobian method, and from the joint PDF we can find marginal of W, and that will get the PDF. So this we define W है ना as this. We define or so a random variable ऐसे लिखता हूँ, a random variable W is defined as this, and so PDF or distribution, and distribution of this random variable W is, so distribution of random variable W is F distribution with mn degree of freedom. ठीक है, so there are two numbers n, m, they are natural numbers actually. So n is a natural number, m is also a natural number. Okay, so what we got? So actually we got W, which is X by M, Y by N. Both are chi-square. Oh, 1 minute, something is wrong. So N, M na. So we have to, so you have to divide by degree of freedom. Okay, so either I should change there or I should change here. So if I write like this, so I have to change it here. So it's a chi-square with M degree of freedom, N degree of freedom. Now it's fine. Okay, so chi-square with, so that will be fine. So X is a chi-square with M degree of freedom, Y is chi-square with N degree of freedom. So then you have to divide by degree of freedom. So chi-square M by M, chi-square N by N. Okay, and then it is Mn. The order is maintained, numerator, denominator. So this has F distribution with Mn degree of freedom. And similarly, if you take 1 by W, so if you take 1 upon W, so what will happen? It will be Y upon N upon X upon M, and that will have F distribution with Nm degree of freedom. Okay, so after doing reciprocal, just degree of freedom interchanges. Then what will be PDF of this random variable? So some PDF is something complicated, but we can define. So now PDF of W जो कि है ना, which is actually F distribution with m and degree of freedom is, so what will be PDF of W? Let me write in terms of X only. And you may write in any variable, W, X, T, whatever you want. So just variable I'm taking X, it's a PDF of W. So it will be again gamma m plus n by 2 upon gamma m by 2 gamma n by 2, then m by n, and then, so it's complicated, so we have to see. I may do mistake. So it's a F distribution, right? So the PDF is like, okay. So m by n raised to power m by 2 into x raised to power m by 2 minus 1. Oh, that's why I was defining like this. So if you take x with this, so you will have 1 upon x. Or you can define like m by n into m by n power m by 2 minus 1. Okay. So, and again 1 plus, this is, so you have to remember, because in the exam you may need this. Okay. So this is the formula actually. Since x is also positive, y is also positive, so ratio will be positive. So support is positive here. Just have written variable x, but is a PDF of W. PDF of W in variable x I have written. This is PDF of F distribution with m and degree of freedom. Similarly, you may write F distribution with m and degree of freedom. So you n m. So you can just replace n by m by n. Okay. So what is the expectation of W? So if you find expectation of W, it will be n upon n minus 2. If you find variance of W, so again n should be more than 2. So, and so variance is a little complicated, no? This is actually, I have taken mn now. So here it is 2n square m plus n minus 2 upon m into n minus 2 whole square n minus 4. Okay. So this is actually variance of that F distribution with n degree of freedom. Okay, if you have any doubt, you may ask. I think, yes, thank you, Saranya. It was mistake from my side. Okay, so it's fine. So basic theorem, you already know all this. You have done, but main is problem solving. If you solve problems, you will understand how these questions are asked. Anyway, then further there are few theorems like I have said, if you take T distribution with 1 degree of freedom, so like I said, this is identically distributed with Cauchy 0, 1. And the second, if you take T distribution with 1 degree of freedom square, so that will be identically distributed with F1, 1. Okay. And the third one, if you see, t distribution with n degree of freedom whole square, that can be proved. Actually, I'm not writing proof here. Proof will be there in book. So just I'm writing things which will help you to solve questions for UGC net actually. So this will be actually f1 comma n degree of freedom. Okay, so like if I take t as t distribution with n degree of freedom, and suppose w is t square, then PDF of w will be f distribution with 1 n degree of freedom. So these are some theorem for large n. So for large n, t distribution with n degree of freedom can be approximated to normal 0 1, or it converges to normal 0 1. Similarly, chi square with n degree of freedom can be approximated to normal with n to n degree of freedom. Okay, for large value of n. So for large value of n, this can be done. So let's try a few questions. Okay, so this was the theory of just sampling distribution briefly, not much in detail. So just the theory of sampling distribution, and so I started class with this topic. So far we have discussed this much. Okay, if we define, so let me define this also. So this will be done. In the next class I will discuss rest part: mode of convergence, weak, strong law of large numbers, and telemetry. There will be 4-5 definitions, and then 3-4 theorems, and that's all, and then few properties or questions that can be done. So what is a characteristic function of a random variable? So you know MGF and a moment generating function of random variable x. So this is defined like this, and the definition is expectation e raised to power tx, you know already. Similarly, the characteristic function is a moment generating function. So I'm writing characteristic function of x. So I may define it like cxt, and this is just you replace t by iota t. Okay, and what is iota t? Achha, I have defined in first class also. So this iota is here. So iota is square root of -1, है ना? This is a complex number, है ना? So iota is imaginary number which is square root of -1. What is the advantage of characteristic function? So like the result is, so MGF may not exist for some distribution. Okay, so MGF may not exist for some distribution, but characteristic function will always exist for all distribution. So characteristic function, I'm writing CF. So characteristic function exists for all distribution or for all random. So any PDF, PMF you take, characteristic function will surely exist. Okay, so you know Euler formula, so that will help you sometime. E raised to power iota theta, so it's the cos theta plus iota sine theta. Okay, so This is just definition. Okay, so this is a definition of characteristic function. In both cases, t belongs to an interval containing 0. So 0 must be in the domain of MGF and characteristic function. Okay. So basically, if you write the property, like if I write, so in the MGF also, if you put t is equal to 0, you'll get 1. Similarly, in the characteristic function, like I have written cxt, so if you put 0, you will get 1. Okay. The third one is, if you take modulus of cxt, so if you take the modulus of this, what will be this? Root under cos square plus sine square, and it's 1 actually. So in general, if you take their modulus, so again you can write it e raised to power iota tx can be written as cos tx. Oh, it will be minus a square plus b square. Okay, 1 minute. So I have to see. So this will be since cos and sine are both are between -1 and 1. Okay, so it is cos t plus iota sine tx. Sine tx. Okay, this you can write if you want. You can write this e raised to power iota tx is cos tx plus. But the property is, if you take absolute value of characteristic function, it will always be less than equal to 1. Okay, for all t. And further, you can write, if you take cx minus t, so what will happen if I define cx minus t? So that will be what? Okay, let me write property. So that will be equal to, you just replace t by minus t. It will be e raised to power minus iota tx. It will be cos minus tx minus iota sine tx, or plus iota sine minus tx. If you simplify further, so you will find it's a cxt conjugate. Complex number, you have to little bit familiar with the complex numbers, a plus iota b. So that conjugate of that cxt, it can be verified very easily. So let y is ax plus b, then how do you write mgf of y in t? So that is e raised to power bt mgf of x at. So in the similar way, characteristic function of y can be written as, what will this? So it's a iota, iota tx. So t will be iota e raised to power iota bx, iota bt, characteristic function of iota at. Can you write like this? So, or no, iota. So iota in the definition, no? So it's iota is in definition. It's a at only. Okay. And like MGF, characteristic function also determine distribution uniquely. So every distribution has unique MGF if it exists. So similarly, every distribution has unique characteristic function. It will always exist. And every MGF correspond to unique distribution. Every characteristic function correspond to unique distribution. Okay. So, okay, non-central, since I'm not discussing non-central, so in the non-central, what happens? What I have discussed was only central distribution. Okay, central chi-square, central t, central f distribution. Actually, all were central distribution. If you define non-central, it can be defined. For example, so like I said, just for the, like, x is normal 0 1, or just z is normal 0 1, let's say. So then z square will have, z square has chi-square distribution with 1 degree of freedom. And now if you take x as normal mu sigma square, then in that case x square has non-central chi-square distribution. So non-central chi-square distribution with 1 degree of freedom. So mostly questions are asked based on especially gate level, so that are asked central only. So that can be discussed, non-central can be discussed, but I don't think that will be required. Okay. So in the just standard normal, square follows chi-square, central chi-square actually. So this is central chi-square distribution with negative term, and this will be non-central chi-square with. So similarly, others can be defined. Like T distribution, we have taken Z as normal 0, 1. You take Z as normal mu sigma square, and then accordingly you can define non-central. I think let's solve few questions, so it will be better. So we have discussed this part. So let's solve some questions. So tomorrow I will discuss this theory. So in one class I will complete. So this theory will be completed, and then I think tomorrow will be my last class. Okay, so this tomorrow we'll discuss. Let's try a few questions. So convergence part, these type of questions we'll discuss tomorrow. For the time being, these are all convergence questions. So for example, you'd see this question. So if you go manually, it will take a lot of time. This is a question of transformation actually. So if I ask you, see, this is the PDF of random variable x. So can you find CDF of random variable x? So what will be the CDF of random variable x? You find, actually, why do we need? So you may ask, why do we need CDF? Okay, so let me first explain why do we need. So there was a theorem we have seen. If you take y as a CDF of random variable x, so that will have distribution uniform 0, 1. So what I'm getting idea here, this is quadratic and this is cubic. So if you find CDF, you may write this as a CDF of that random variable. So this is a PDF of x, you find CDF of x, and you will see that CDF is some multiple of this, or you can write this as a in terms of CDF, and then it will be easier to find expectation. The other way is, so one of the idea I'm giving, it's a simpler way, or you can say not simpler way, it's a traditional way is, you just find, so you need expectation of gx, so you know how to find expectation of gx is integration gx into PDF of x. This is the other way. If you can go through this, this is, so then you can find answer through this. Let's take gx as this, and then you find. So that is a one way. Easier will be this one, what I'm saying. So since PDF is given, and this is cubic, so that will be in terms of that, and the intention of question seems like that. So you please find CDF and tell me what is expression of CDF. So CDF actually is, how do you find CDF? You integrate 0 to x. This is 3 by 13. If I integrate it, multiply it, so it will be x square minus 10x and plus 9. So dx, but x is also there. That's why you change variable. Okay. So you just simplify it. So it will be x cube by 3, 5x square, and then 9x. Okay. And if you put 0 to x, it will be this only. Okay. And that's why we change variable here. So x and x are common. That's why. So you get CDF of x like this. So can you fix that? So this is x cube minus 15, x square plus 27. So if you multiply by 3, so I can write it, multiply by 3, so divide by 3. So this 3 you multiply inside. So this 3 if you multiply inside, it will be x cube minus 15x square plus 27x. And this is exactly same what is here. Okay. So now, so what I'm claiming, this is the one way you may go through this. So I'm using this way. So if I defined y as, this is CDF in term. If I defined y as CDF of x in terms of x, so that is 1 by 13 x cube minus 15x square plus 27x. Okay, and so that is, this will have distribution uniform 0 1. Okay, so I just want distribution of only this. So suppose this is, let's say, w. So one w by 13 has this distribution, so w will have 0 13. Okay, so then from here, x cube minus 15x square plus 27x will have a uniform 0 comma 13 distribution. So expectation of x cube minus 15x square plus 20, oh, I think it's fine now. So it's this one will be a plus b by 2. It's a 13 by 2. So the answer part here, if I find, so this equals 4 by 3. So answer will be 4 by 3 times 13 by 2. So is it, you can cancel by 2. So it's what? 26 by 3, is it? So this is 26 by 3. Check it. So answer is 26 by 3. So we calculated this here, and you just put it there, 4 by 3 into 13 by 2. So is there any problem? You see, if you have problem, please ask. So we just calculated CDF, distribution of CDF uniform 0 1. This is a transformation, that is a probability integral transform, and then based on that we calculated it. Okay, so we have discussed sampling. So let's say some sample type question. It's a sample. Do we find any sample? So testing question. So sample will be like more of testing. Okay, this is based on actually let's solve this question. So we have discussed order statistics. Have we discussed order statistics or not? So order statistics, you know. So if you see order statistic, these are order statistic corresponding to this. So each xi follow uniform 0 theta. So xi upon theta will follow uniform 0 1. Okay. Then there is a theorem. What do you need? Second order statistic. So if you take second order statistic based on this will follow beta first kind. So what is the theorem? So theorem I'm using this. So let x, x1, x2, xn. It is IID uniform 0 1. Then rth order statistic will have distribution beta first kind r comma n minus r plus 1. This theorem I'm using here. Okay, so this is 0 1. So the second order statistic will be 2 comma 5 minus 2 plus 1. 5 minus 2 is 3 plus 1, 4. So it's a 2 comma 4. Okay, so it's a beta 2 comma 4. Now you can easily find expectation of second order statistics by theta. So what is the PDF of beta? So it's a 2 upon 2 plus 4. So it's a 2 by 6, which is 1 by 3. So if you do cross multiplication, 3x2 will be theta. You know definition of unbiased estimator. So T is called unbiased estimator of theta if expectation of T is theta. So expectation of this is theta, yes. So this statement is a true statement. I just calculated this because of this transformation, although this is a question of estimation. Okay, and this is if you see here uniform 0 theta, the fifth order statistic is complete sufficient estimator, and then unbiased given sufficient is more efficient estimator than the unbiased alone, and that is a theorem is called Rao-Blackwell theorem, and that's why this is also true statement. So both are true statement. So this we have done this, we just wanted to calculate expectation actually, but this question is of estimation. Anyway, both statements are true. So to understand this, you need to know Rao-Blackwell theorem. Okay, so I tried to use transformation, that's why I started this question. Okay, again this is same based on Rao-Blackwell theorem. So more of estimation questions are there actually in sample. These are all MLE and all that. all testing. This is a multivariate normal, I think. This is a confidence interval. So all are estimation questions actually. Complete, sufficient, testing, method of moments. You know, empirical distribution function. So it's all confidence interval. So when we will not able to find directly this type of, but yes, this type of questions can be done. So these are actually questions based on transformation. So for that you need to know theorems, है ना? So there are good number of theorems in the book VK Vadgi and Saleh. So there you can find good number of theorems. You write it all definition, all theorems, and then you try to use in questions. How will use that theorem in questions to solve entrance problems. So like this is the question that we are starting. This is based on a theorem. So I will write a theorem and then you will know. So they have given you x1 है ना, x2 x7 with the sample from normal 0 theta. Okay, so you know abhi just we have discussed. So xi is normal 0 theta. So xi upon root theta will be normal 0 1. Xi square upon theta will be chi square 1, and chi square 1 is gamma n by 2 1 by 2. So chi square 1 is this. So I'm saying xi square upon theta will be this. If you define both numerator and denominator by theta, so it will be like x1 upon theta whole square, x2 upon theta whole square, denominator summation xi upon theta. Oh, 1 minute. So theta is outside, right? So theta is outside. So I'm dividing numerator denominator by theta. The x1 square by theta, x2 square by theta, summation xi square by theta, I from 1 to 7. Okay. So now okay, so what I'm saying, this is chi square with 1 degree of freedom, chi square with 1 degree of freedom. So adding will be chi square with 2 degree of freedom. This is chi square with 7 degree of freedom. But you know, F distribution will not be like it is written F distribution. So you see, recently we have written a theorem. So x is chi square m, y is chi square n, and they are independent. Then x by m, y by n will be f m n. But I'm saying this theorem will not work here. Why? Because here numerator and denominator should be independent. Here numerator and denominator are not independent. They are dependent actually. Okay. So, okay, we should search sampling. Okay, fine. Okay. So I'm saying this theorem will not work here. Why? Numerator and denominator are not independent. That's why. But what you can do? So there is again other theorem. So I'm writing one theorem, and so there are many theorem related to each distribution. So writing all theorem will take time. So I don't have much time, है ना? So we cannot give you. I mean, I'm not allotted that much time to give, है ना? Write all theorems. But you can find in VK Vadgi book there are good number of theorems. You read each theorem, each definition, make your notes, and then solve question based on that. So this is a theorem in the gamma distribution topic of VK Vadgi. So let just for the time being x is, or let x is gamma alpha 1 comma beta, and y is gamma alpha 2 comma beta. Okay, So, and both are independent. So they are independent random variables. Then, so the first part is x1 plus x2 will be gamma alpha 1 plus alpha 2 comma beta. Second part is x upon y will be, so they are independent, okay. So it will be independent ratio is what? Beta second kind, alpha 1 comma alpha 2. And the third part, x upon xy will be, I think there is something change. So what will they follow? X upon x plus y is what? Is it beta first kind? Okay. If I divide by x, yes. So y upon x. Y upon x is alpha 2, alpha 1. So if you divide by y, okay. So I think that is beta 1, that is beta 2. I have to see once. So it is beta alpha 1 comma alpha. Both are different beta actually. So tell me which are this. So these are actually, this will be used. And I'm writing just now, they are not same beta, they are different beta. I'm writing just let me see. So the idea is x plus y and x upon x plus y, they are independent random variables. That will be used there. And further, x upon y and x plus y, they are independent random variables. Okay. So tell me, in the second part, which beta will be used? Beta first kind or second kind? Or in the third part? So which part will use which kind of beta? Anyone who can help? No one. So this is actually beta second kind and this will be beta first kind. Okay. So this is a theorem you can use, and this theorem will help us to decide next part, next question actually. So the question is k is ratio. So it's kind of your you understand like x upon y. So this is x upon y, but see, they are not independent. So you can write, okay, this is x and the remaining one you can tell y. So it's a x upon x plus y kind. So it's a x upon x plus y kind. So that k is x upon x plus y kind. So that will be beta first kind. So numerator is chi square 2. So chi square 2 is gamma 1 comma 1 by 2. So it will be 1 and x plus y. So y is after 3 to 7. 3, 4, 5, 6, 7. Okay. So it's a 5. 5 random variable. So chi square 5. Chi square 5 means gamma 5 by 2, 1 by 2. So it will be 5 by 2. Check it. Now this is beta first kind. So the expectation of k will be what? So they are asking na, okay, here k square you want na. So expectation of k is third part I'm solving currently. So it's a mean is in the beta first kind, what is mean? It's alpha plus beta upon 2. No, it's alpha upon alpha plus beta. So alpha upon alpha plus beta. So it's a 2 by 7. Okay. And variance, so you find mean and variance from beta 1, beta first kind, and then you can check this based on this. Okay, let's come to this. K and this are independent. So k is x upon x plus y and this is x plus y. So x upon x plus y, and this is true statement. This will be f distribution. No, this is false statement. So this is true statement, this is false statement. This will not be f. What will be this? So this will not fit on this. Actually, they are talking about this theorem, but that cannot be fitted. And I think you just check it. So what is the formula of variance? Alpha, beta, then alpha plus beta plus 1 and alpha plus beta whole square. Is it? You put it there, and then using these two you can find part third. I think that's all. So that's all for today. Thank you. We'll discuss next one. I will request you to solve a lot of questions as much as possible. So tomorrow will be last class for me. So tomorrow I will discuss this part, and then some question and theorems, definition, theorem, few examples. We'll discuss on this, and that's all. Okay. So thank you for today. We'll meet tomorrow.